you see that well from there?
Yeah,
Just
good.
making sure.
I got it.
Okay. Can you guys hear me well? Does the microphone work? Kind of. Is that better? All right. Can the people in the back hear me? Cool, thanks. All right, guys, so just before we start anything, these questions don't actually belong to me. They're from the ACS manual, so I'm just gonna like go over the questions, break them down one by one. And yeah, just try to approach whenever you're taking the exam the same way. Try to like eliminate the answers that you think are not right, and then hopefully that works. If you have an understanding of like general mechanisms, that should help you too. So yeah. Before we start, do you guys have any questions about the exam in general? Someone was asking me if you guys need a Scantron. I'm actually not sure, but I would take one just in case. Okay, I know for Dowdy you need one for sure. I'm not sure about Fraser. Yes? Yes, it should be timed. I don't think they're going to give you like the full 3 hours, I think, that finals usually have. I think it's only like 180 minutes, and that should be it. Yep. Any other questions, guys? Cool. Also, I forgot to bring my glasses, so if I don't see your hand, try to like wave at me. I don't know. All right, so first question. If you guys need me to move it up, also let me know. Okay, so what is the IUPAC name for this compound? So usually I don't like how it looks when they have like the carbons all drawn out. So I draw the skeletal structure and then from there I name it. So here I have 1, 2, 3, 4, 5, 6, 7 carbons. So there's my 7 carbons. On number 2 I have a ketone. And then on 4 there's an alcohol. So 1, 2, 3, 4. OH. Cool. Is everyone good with that? Make sense? All right. So if you were to name it, are you guys, do we name it from right to left or left to right? Right to left, right. So why do we name it right to left? Ketones have higher priority than alcohols. So I think, at least for Dr. Dowdy, at some point this semester he had a PowerPoint with the priorities listed on a table. For Fraser, I don't think he ever did that, but there is a chart on Google. So if you guys are interested, maybe for naming, I would memorize that chart. It helps a lot. So in this case, we have 1, 2, that's the ketone. So on carbon 2, we have a ketone. 1, 2, 3, 4. Should be 4 hydroxy. And then on 5, we have a methyl. So based on that, what do you guys think the answer is? Right. Any questions? Cool. All right, so second question. Another naming question. So they actually have it nicely drawn over here, so I'm just going to number it using that. So should we start from this side or from this side? Right, so 1, 2, 7. So on number 2, we have a hydroxy group again. Number 5, we have a methyl. And then our biggest chain is how many carbons? 7? Okay, so it should end in what? Heptanol, because we have an alcohol. So we can automatically discard these two. We have C and D. Between C and D, which answer do you guys think is correct? D? Awesome. Does anyone have any questions about this? Easy so far? Okay. All right. So we're going to look at this one first. It's another naming one, so same thing. For me, it's easier to just draw the skeletal structure, so I'm going to do the same thing again. All right, so in this case, are we going to number it from right to left or left to right? Right to left? Awesome. So why do we name it right to left? Although this one gives us a lower number, why would we name it right to left? Because we have a hydroxy group, so it has a higher priority than a regular methyl. Does that make sense to everybody? Cool. So 1, 2, 3, 4, 5, 6. So we have 5,5-dimethyl and our hydroxy on number 3. So knowing that, what's the answer? Cool. Any questions about this one? That's a good question. So from right to left, although from left to right you have the lower number, hydroxys usually have a higher priority than methyls. So that's like kind of like the table I was talking about earlier. If you were to have an alcohol versus a ketone, ketones usually have a higher priority than the alcohol. Sounds good? All right. Any other questions? Cool. All right, so number 2. Another naming question. So in this case, what do you guys think is going to be the parent? Is it going to be the OH or the nitro? OH, okay. So this is our parent. And then from there, do we go clockwise or counterclockwise when it comes to numbering? Counterclockwise? So why do we do counterclockwise? Awesome. So we want always the lower number when we're numbering a cyclic structure. So we're going to go to the left. So 1, 2, 3, 4, 5, 6. And then it's always in alphabetical order, so that's why they have the bromo first. So we can cancel this one and that one. And so bromo's on 4, nitro's on 3. Therefore, the answer is A. Make sense? Question? Instead of what? Because usually, I don't know if you remember, but towards like the beginning of the semester, we had styrene, toluene, phenol, and all of those groups. So phenol is usually the parent. And then also, like since we have the chance to look at the answer choices, they all end with phenol. Did I mess up? Yes, my bad. So yeah, it's not A because A ends in phenyl. What's phenyl? Right, it's a benzene ring. My bad. Any other questions? Yeah.
Why wouldn't it be
B.
Because isn't the bromine pair with the alcohol, and then the nitro group is also made up to an alcohol?
So when we use paramethane ortho naming, it should be usually with 2 substituents only. So if you have 3, it can get a little confusing. So that's why you use the numbering over paramethane ortho. Good question, though. Any other questions? Cool. All right. So which is the structure of Z3,5-dimethyl-3-nonene? All right, so what I do when I do these questions, I draw it myself, so I don't even look at the options. I would just go ahead and draw it first. So we have nonene, so we know it has 9 carbons. 1, 2, 3, 4. 9 carbons. And then we have two methyls, and then it's Z. When it says Z, what does that mean? Right, so the groups with the higher priority are going to be on the same side. If it was E, then it would be opposite side. So keep that in mind. Z, same, E, opposite. So in this case, we want C. And then it's 3 nonene, 1, 2, 3. Boom. Is that Z or is it E right now? E, right. So if that doesn't work, what could we do to fix it? So we can rotate these two. So we could have and then what looks like that? See? Right. Does that make sense? Yes. Which one? Okay. Are you sure?
Yeah.
All right. Any other questions? Yeah. Thanks. There you go. Thank you. Anything else? Good? Awesome. All right, so next question. This should be one of the easier ones, but sometimes we forget because we're not exposed to this all the time. It's back in like Gen Chem. So in which of the Lewis structures would the iodine be assigned a formal charge of +2? So who remembers how to calculate formal charge? Right, so valence electrons minus bonds and then, yep. So the way I look at it is just electrons touching my atom, so it's just easier for me to remember. So electrons. All right, so if we look at A, this one has 1, 2, 3, 4, 5, 6 around it. And then valence of iodine should be 7 minus 6 plus 1, so that doesn't work. This goes out. This one has 1, 2, 3, same thing, goes out. 1, 2, 3, 4, 5, 6, 7. That should give us a formal charge of 0, so that doesn't work. Therefore, the answer is B. Good? Any questions? All right. Yes. What's up? Whoa, hold on. Let me get closer because I can't hear you. How do I know it's 7? So iodine is on the halogen group. So based on the group of the periodic table, they should give you the periodic table on the exam. Yep. Good question. Any other questions? Yes.
Can you just go back up to the last one, number 5, real quick?
Yeah. Yes. So it's the higher priority though. So we're looking at this one because when I did this one at first, our higher priority is on this side and then this whole chain over here. So if we look at that one, they're on the opposite side and that's not what we want. So that's why I rotated it so that this larger group and this one would be on the same side of the double bond. Mm-hmm. Because we're comparing this one and that one, not these guys. Does that make sense? Yeah. Okay. Yep. Any other questions? All right. Is everyone good with that one? Cool. Okay. So this question, this goes back to the aromaticity chapter, which wasn't too bad. I think it was like one of the easier ones in Orgo 2. So which structure has exactly 6 electrons? 6 pi electrons. So how many electrons do we have here? 8, right? So we have 1, 2, 3, 4 times 2, 8. On this one, how many do we have? 6. 1, 2, 3 times 2, 6. And then on this one, 4. Are you sure? It is fully conjugated, and then it has 1, 2, and then is the O participating in the p orbital? Right. So I should give it 6. So these two should have 6 pi orbitals. Pi electrons, my bad. Does that make sense? The only confusing one on this problem maybe would be number 3, knowing that oxygen is actually contributing, the lone pairs on oxygen are contributing to the conjugated system. Do you guys remember that from class before? Okay, good. So if the pi bond was actually touching that oxygen, would it be contributing? No, right. So since it's not touching it, it is in the p orbital. All right, so therefore the answer should be C. Any questions? No, yes. This one right here, it doesn't make part of the system, so that's why you don't count it. It should only be 1 pair of electrons. Good question, though. Any other questions? Okay. All right, so which represents a pair of resonance structures? So if we look at the first one, they are moving this pi bond over here, but is that allowed? Can we do that? No? Awesome, why not? Exactly, so we already have 3 hydrogens over here, so you can't really move that pi bond there because it would have more than it needs. Okay, so A is not the answer. B, they are, what are they doing? Okay, they're moving this up, this down, this over here. Is that allowed? Is everything fine on that one? Looks good? Okay, so that should be the answer. I won't even bother checking the rest because that's automatically correct. Any questions? Yes? Mm-hmm. Right, so I'm just going to erase this. So since they're giving you CH3 initially, you couldn't move this pi bond over here because then it will have CH3 plus a double bond. Yep. Any other questions? Cool. All right, this one's kind of similar to the one we were doing before. So what is the hybridization of the orbital containing the unshared pair of electrons on the nitrogen atom in pyridine? So what do you guys think? sp2? Awesome, so why is it sp2? Awesome, so it would break the aromaticity if it's not in the p orbital. Also, the pi bond is actually touching my nitrogen, so I know it's not going to contribute to the system. Make sense? Any questions? Yeah. This one? Okay. Yes. Did everyone hear that? Just to like repeat it again. So if it's not touching the atom that we're looking at with the lone pairs, then the lone pairs would contribute to the system. Okay? Any other questions? No? All right. All right, so which structure is not aromatic? So what do we need to look at for us to know if it's aromatic or not? There's certain things. Huckel's rule is one. What else? It has to be fully conjugated, cyclic, and planar. So I'm just going to write it down. All right, so it's asking for which one is not. So A, is that aromatic or not? Nope, right. So what is Huckel's rule? Awesome, so 4n plus 2, n being what? I heard number of pi bonds. Do you guys all agree with that? No? Okay, so it should be any number. So it really doesn't matter what number you plug in as long as you get, whatever number you get, that should be the number of pi electrons you're allowed to have in that structure. Okay, so in this case, if we plug in 0 for n, you could get 2. If you plug in 1, you get 6, 2, 10, and so on. So if it satisfies any of those numbers, then it should be aromatic. So if we look at the first one, you have 2, 4, not a number that works, so that's the answer. Any questions? Yeah. Yes. So Huckel's rule is this, right? 4n plus 2. And then n being any number that you want to plug in. So 0, 1, 2, 3, whatever. Okay? So if we plug in 0, you get 2. If you plug in 1, you get 6, 10, and then it just goes up, right? So if we look at how many pi bonds we have here, how many electrons? We have 4. Is that one of the numbers that we have over here? Right. So it doesn't satisfy Huckel's rule. Does that make sense? Cool. Any other questions? All right. And then this one looks a little funny. So how do you know it is aromatic? because that one used to trick me a lot. I don't know, for some reason. It just looks simple, and I thought it wasn't, but it is. So it has 2 pi electrons. That plus sign means that it has an empty p orbital, so that's why it's still fully conjugated. Okay? Make sense? Cool. All right, this is kind of like an Orgo 1 question. So which carbocation is the most stable? So as far as we know, what is the most stable carbocation that we can have? Tertiary before that, though. Allylic, awesome. So in this case, we're going to look for the allylic carbocation. So is this one allylic? No. Automatically out. Is this one allylic? Yes, no, maybe. So we have this pi bond over here. If we resonate it, it is allylic. This one makes no sense. So between A and C, which one do you guys think is the answer? Yep. So since they're both allylic, how else did you determine that it was the most stable one? Say that again? Yep, so it has another methyl group, so that stabilizes that positive charge better. So that's why it's more stable. Makes sense? Question? Yeah, so both of them are allylic, both A and C, but then A has that extra methyl group next to it, stabilizing a little more. Yep, yep. Any other questions? Cool. All right. So these I'm going to redraw them because I don't like seeing that. All right, so the question is, what is the order of acid strength from strongest acid to weakest acid? So 1, 2, 3, and 4, which one's the strongest one? 3. All right, do you guys all agree with that? Cool. So start with 3. What goes next? 4. Okay, so why between 3 and 2, why did you pick 4 first? Yep. Cool. And then from there, it should be a little simple, so it should be 2, 1. And then that's answer C. Yes? Yeah, so on number 3, we have fluorines, which are more electron withdrawing than a chlorine, right? Because if we look at the periodic table, it's more electronegative than chlorine. So our number 1 should automatically be this one, because it's the one closest to the OH. So when you look at the conjugate bases, so if I were to get rid of all these hydrogens, we're going to end up with a carboxylate, right? So if we have a carboxylate, it's going to be negatively charged. So we want something that's going to pull away that negative charge throughout the whole structure. All right, so if we have the fluorines, which are closer to that carboxylate, it's going to stabilize the charge a little more. So on this one, we have fluorine. This one, it's still close, but it's chlorine. But then it should still be more able to withdraw that electron density than something that's 1 carbon away. Does that make sense? Okay. Good question. Any other questions? All right. How do you guys think it's so far? Is it hard? Not too hard? It's pretty fair. There's a lot of questions in the ACS that you're just going to answer like in 2 seconds. They're not too bad. All right, so identify the weakest acid. So same thing, we're going to look at the conjugate base. So if I were to get rid of all these hydrogens, the more stable the base, the what the acid? The stronger the acid. So in this case, which one would be my strongest acid? C, strongest. So if we look at the negative charge, we want to make sure that that electron density goes through the structure, right? So out of these, which one is electron withdrawing? Right, so B should be the strongest acid just because I'm able to stabilize that conjugate base a little more. So therefore, the weakest acid should actually be C. Does that make sense? Yeah. So is the mic working fine? I feel like I'm not loud enough. I don't know. don't know. Hopefully that works. So, all right. A doesn't have any electron withdrawing or donating groups, so we can automatically discard it. Okay? So that's kind of like our structure that we can use to compare everything else to. All right? So A is not the answer. B has an electron withdrawing group, right? So it has nitros. What else would be electron withdrawing from what you guys remember in class? Stuff like carboxylic acid, anything with a carbonyl carbon should be withdrawing. So we don't have any of those right here. We do have a nitro though, and that's withdrawing. That's one of the most withdrawing ones actually. So if we have this going on, which is a conjugate base, if we have an electron withdrawing group, it's going to take away that negative charge and kind of distribute it throughout the whole structure. All right? Does that make sense so far? Okay. So if it's withdrawing and it's stabilizing that conjugate base, what does that tell us about the acid? It should tell us that it's stronger, right? So the more stable the conjugate base, the stronger the acid. So in this case, if it was asking for strongest acid, then B should be the answer. But then since it's asking for the weakest, it's C. Because C would be donating electron density to that group instead of withdrawing. Because it has lone pairs on the oxygen, so via resonance, it should donate electron density to the ring. Okay? And then D is also withdrawing, but is not as withdrawing as the nitro group. Make sense? Any other questions? All right, so the answer is C. Cool. This one has like a full paragraph, which is a little annoying, but we'll read it. So the imidazoles ring system, which contains 2 nitrogen atoms, is found in the amino acid histidine. Which statement is true regarding the basicity of the 2 ring nitrogen atoms? So we go back to that same concept we were talking about earlier. So in this case, is nitrogen 1, are the lone pairs contributing to the system or not? Okay. So lone pairs not contributing. What about this one? Yep, cool. So if the lone pairs are actually contributing to that aromatic ring, is it going to make it more basic or less basic? Less basic, awesome. So why does it make it less basic? Exactly. And then if we don't have those lone pairs, then it's not actually going to function as a base as much as this one would, because it has those lone pairs free to interact with something else as a Lewis base. Okay? So if we look at the answer choices, both are strongly basic since the ring is aromatic. Not true because one contributes, the other one doesn't. B, the nitrogen atom labeled 1 is more basic than 2. That should be true because number 1 is not contributing to the system, number 2 is. So that should be the answer. Does that make sense? Any questions? Yeah. If the double bond is directly attached to the nitrogen, then it's not contributing. If you look at this nitrogen, no double bonds are actually touching it. Any other questions? Yeah. Yes, it's more basic than the one that's actually giving those lone pairs to the aromatic system. Yep. Any other questions? All right. So, which is the most stable conformation for cis-1-bromo-3-methyl cyclohexane? So this goes back to orgo 1. So what is more stable? Having everything axial or everything equatorial? Equatorial, awesome. So let's look at each one. This one has up carbon, axial, and then this one's an up carbon axial, so they're both axial. For B, we have an up carbon going down, so that's equatorial. Up carbon going down, equatorial. Both equatorial. For this one, up, down, just one of them is equatorial. And then for this one, down, up. So just one equatorial. So in that case, which one would be the answer? Any questions? Does that make sense? All right. Newman projections. You're probably going to see like 2 or 3 questions on Newman projections. For some reason, they like them. So if you need to go back to study those, definitely do that. It's back in Orgo 1. That and Fischer projections, you'll see like 100%, no doubt. All right, so which Newman projection represents the most stable conformation of 3-methylpentane when viewed down from the 2 to 3 carbon-carbon bond? So what I do for these problems, once again, I redraw this because I don't like how it looks. So 1, 2, 3, 4, 5. And then it has that carbon there. And we're looking it down from carbon 2 to 3. So if we look at it this way. Make sense? Okay. So if we're looking it down that way, our front carbon has CH3 coming down, and then we have 2 hydrogens. And then for this carbon, we have CH3, that FO coming out, and then an H. So that's me just kind of putting them in a random position because they're not really giving us stereochemistry for us to know where to put it. Okay? So if we were, they're asking us for the most stable one. So what would give us the most stable conformation? Something that has a lot of steric hindrance or something that doesn't have steric hindrance at all? Right, less steric hindrance. So if we look at our options, this one has 2 methyls right next to each other, but then the biggest group is farthest away from this methyl, so it could work. It's not that sterically hindered. If we look at B, we have everything pretty close to each other, so it's in the gouge conformation, and we don't really want that. Okay? So remember that there's gouge and anti. We want anti, because it should be more stable than a gouge conformation. So this looks kind of sterically hindered, so I don't think that's the answer. And then for this one, these are pretty close to each other again. And then this doesn't even make sense because it doesn't represent the Newman projection. So D we can discard automatically. And then between these two, which one is the more stable one? Yep. Any questions? Why is it A? Okay, so if we look at the groups, the biggest group is furthest away from the methyl groups. So that makes it more stable. If they're closer, kind of like in this example over here, then they're all like trying to be in the same position. We don't want that because it makes it less stable. Good question. Any other questions? How do you guys feel about Newman projections? Like if they give you a structure and then you have to draw it in a Newman projection, are you comfortable with that? No? Yes? That's a good question. So that's what they told us in the problem. They said view down from 2 to 3, right? Okay, so just make sure you read well when you're taking the ACS. They're going to try to trick you with nomenclature a lot because nomenclature are usually the easy points. So they're probably going to throw something really random at you that you really just have to like read well. So I heard that a lot of you are having trouble with Newman projections, so I'm just going to give you like a quick example, if that's okay with you guys. All right, so that should be fairly simple. So we're going to look at it from this angle. All right, so this is going to be our front carbon. So we draw out the first circle. Is going to have that. So this dot over here represents this first carbon that we're looking at because we're looking at it that way. Okay, so if it's on a wedge, it means that it's coming out of the paper. Therefore, it's going to be on our left. So we have bromine. Hydrogen is going to be behind the paper. It's going to be on the right. And then it should just be CH3. Does that make sense? It's a little hard to view it, but hopefully it makes sense. Okay. And then now we have to finish the rest of the structure. So if it's a hydrogen, it's going to be behind the paper, therefore on the right. So hydrogen. And then this is going down because it's on the plane. and then this ethyl group is on a wedge, goes to the left. Does that make sense? Do you guys have any questions? Whoa, my bad. Yeah. If it wasn't? Right, so I'm gonna go back to that one really quick. So this one didn't have any stereochemistry, but then the only thing they're trying to like test you on is knowing if they're close to each other, would it be sterically hindered or not? So it doesn't really matter. As long as you know, for example, that this one's not a Newman projection at all, then you should be okay. Yep. Are you guys good with this though? Because that's pretty basic. So if you have that straight, you're good. Okay. Fischer projections. So I don't know. Dr. Dowdy did talk about this. I don't know about Fraser. I don't think so. Not much. If you're not strong in Orgo 1, then this is not going to really make sense either, but I'll go over it. So which statement about these Fischer projections is correct? So they're asking us about stereoisomers and stuff. So for number 1, I'm going to redraw it. Okay, so in Fischer projections, have you guys ever been introduced to Fischer projections at all? Like, have you seen them? Okay, cool. So in a Fischer projection, everything on the vertical line is going to be on a dash. Everything on a horizontal line is a wedge. Okay, I don't know if that's new to you guys, but everything on the vertical line is going to be a dash, and then everything on a horizontal line is a wedge. I'm going to write it down. So vertical dash, horizontal is a wedge. All right, so every intersection should be a chiral center. So if we look at this one, this should be our highest priority, kind of like assigning R and S. So it should be our number 1. And then between this one and this one, that should be our number 2. This should be 3. So why do you guys think this is number 2 instead of that one? Right, so this one's directly attached to an OH group. This one doesn't really have anything else. So 1, 2, 3, we follow the numbers, that's counterclockwise, but then since our hydrogen is on a wedge, we need to flip that. Okay, so this should be actually S. Yes, so who asked that? All right, so if it's on a wedge, we always want to flip it. So when we're assigning R and S, our hydrogen also always has to be on a dash. Okay, so since it's on a wedge right now, we need to flip it once we get that priority assignment. So this is our 1. This carbon right here should be 2, and then this one's 3. Right? And then if we follow the numbers, then it's going to be counterclockwise. If it's counterclockwise, it's S. But then since hydrogen's on a wedge, we need to flip it. I get what you're saying. R. Question? Hydrogen's on a wedge. So every horizontal line is always going to be a wedge, at least in Fischer projections. They just don't show it. But if I were to show like the actual dashes, it would just look weird, but I'm going to do it anyways. So that's kind of what the Fischer projection is representing. Just that they don't really draw that. They just like leave everything on a line. Okay? Does that make sense? All right, so let me just double check this. So 1, 2, 3, counterclockwise, you flip it, it's R. All right. And then we have this one. So our number 1 should be here. Number 2 is up, and then 3. If we follow the numbers, it's R, but then we have to flip it because hydrogen's on a wedge. So we get S. Is everyone good so far with that? Okay. So that's for number 1. For number 2, we're going to do the same thing. So this is our 1, 2, 3. If we follow the numbers, it's counterclockwise, but we have to flip it, so that's R. And then for this one, 1, 2, 3. Counterclockwise, we flip it, it's R. So if we compare both of them. This one has R and S. This one's RR. So if we're changing only one stereogenic center, what does that mean? Diastereomers. So should be D. Yes. Yep. Because hydrogen is always, I don't know if it's always going to be on a wedge, to be honest, but it usually is. I don't want to say always, but usually you have to flip it. So remember when we were assigning R and S, you always want your lowest priority group to be on a dash. So if that's the case, if you're assigning priority and you see that the lowest group is on a wedge, then you have to flip it. Okay? I saw a hand. Yes?
So how are 2 and 4 not also identical?
2 and 4. We can assign the configuration for 4 just to kind of like visualize it if we want. We can do that. Right, so I always look at it that way. Whenever, back in Article 1 even, when they asked me to do enantiomers and diastereomers and all that, I would always assign priorities and R and S. If everything is different, then you automatically know it's an enantiomers. If only one is different, then it's diastereomers. It takes a little time, but it's a little easier to visualize.
Identical in terms of R and S.
Right. So if they're all, if the one and number 1 is RR and then 4 is also RR, then they would be identical.
Okay, that's what they mean by identical.
Yeah. Meso compound is when you can draw a line of symmetry between the compound, and then both halves are the same thing. I don't know if you guys remember that. But it's usually 2 chiral centers or more, and then if you can draw a line of symmetry and they're both the same, then it's a meso compound. Usually achiral as well. Yep. Any other questions? Yeah. I don't think, when you're saying if something's meso, it's not really for comparison, kind of like when you're comparing enantiomers and diastereomers. They would say something like C, for example, when they're saying like 2 is a meso compound, it's not, but then if they said 1 is a meso compound, then that would be an option. Right, because there would both be, if you draw a line of symmetry, then both halves would be the same. Exactly, yep. Any other questions? Yeah. Yeah, so meso compound, you usually have 2 chiral centers or more. You can draw a line of symmetry and both halves are the same. And then they're usually achiral. That's all I got. I don't know if anyone else has anything to add to that.
You have 2 chiral centers and both of them are the same orientation as well?
I believe so, because it's achiral. So it should be the same orientation, so they should both be R or S, as long as, or cis or trans is a better way to put it. So if they're both cis and you can draw a line of symmetry, both of the halves are the same. But then if it's trans, if you draw a line of symmetry, it's not going to be the same unless you can rotate it and make it meso. Does that make sense? Okay, so if it was like, if it wasn't a ring, if it was just like something like, something like that, right? You can draw a line of symmetry, meso, but then if you had that where they're kind of like opposite to each other, you can still rotate this bond and make it a meso. So it really depends. As long as you can draw a line of symmetry in the middle and both halves are the same, it's a meso compound. You would rotate the single bond. If it was a pi bond, you can't rotate it. But single bonds, you can always just flip around and mess around with it. Right, if it's cyclic, then it's going to be trapped in the same, right, orientation. You can't really flip it or anything. Yep. Any other question? Okay. Does this one make sense a little more to you guys? All right, thank you. So, number 9. What would be the stereochemical classification of the product of this reaction? So we have this, And so what's going to happen? What kind of reaction is this? Hydration? Addition? Okay, addition, and then what else about it? Do you guys remember hydrohalogenation? Okay, so it's hydrohalogenation. So the double bond is going to go ahead and take up that hydrogen, form a carbocation, and then Br adds right there. So that's pretty much what's happening, okay? And then the question is, what is the stereochemical classification of it? So when we have hydrohalogenation, are we adding the two groups on the same side, or are they going to be anti to each other? Or both? When we're adding the hydrogen and the bromine on this example, are we going to add them on the same side of the compound, or are we going to add them on opposite sides? Opposite, right. So that's going to give us a racemic mixture. So that's why it's D. Syn can also happen. So for hydrohalogenation, you can get syn addition and anti-addition as well. Okay, so racemic mixtures are when you have 50-50 of the enantiomers. So you can have either one. That's a good question. Does that make sense, guys? So when you have, since we know hydrohydrogenation can be anti, then hydrogen can go ahead and add on a dash, while bromine can go ahead and add on a wedge. But then we could also have the opposite. So bromine can add behind the plane, and then hydrogen can add above. So that's why we get the racemic mixture. Right. Mm-hmm. Does that make sense? So for hydrohalogenation, you can get syn and anti. For halogenation, I don't know if you guys remember, but it's only anti. So if it starts with a halo, anti always. If it starts with hydro, syn and anti. If it's hydroboration oxidation, only syn. It's back in Orgo 1. I don't know if you guys remember that. Yeah. So if it starts with hydro, it's always going to be syn and anti. If it starts with halo, like halogenation, halohydrogen formation, anything that starts with halo, it's always going to be anti. And then if it's hydroboration oxidation, which is kind of like an outlier to everything, it's only going to be syn. Yep. Yeah. Yep. Any other question? Yeah. Hydroboration oxidation. So that's when you add a hydrogen and an OH across a double bond or a triple bond. So when that happens, you can only add its syn. So both of them would go either on a wedge or a dash. Yep. Any other questions? All right. What is the expected major reaction pathway for the following reaction? So they're asking us whether it's elimination 1 or 2 or substitution 1, 2. Okay? So we have a good leaving group, which is typical of SN2 reactions, or E2. And then we also have this base / nucleophile, right? And then is that base bulky or not? No? Right. So what would make it bulky? Right. If you had like a terbutoxide or something really branched, then that would be bulky. And then if that was the case, then it would be E2. But then in this case, since we don't have something bulky and we have a good leaving group and it's also primary, it's SN2. Does that make sense? Any questions? Yeah. So if it was E2, then the base would be very bulky. But then in this case, it's not. So if it was bulky, it would have a terbutoxide or anything that's really, really branched. Okay? But then they're not giving us that, so we know it's not A. And then looking at everything else, we have a good leaving group, which is Br, and then it's also primary. So if it was one of the E1 or SN1s, then it would be like a tertiary having a carbocation formation and stuff. But then in this case, we have a primary, so that's why it's SN2. Can I draw the product? That should be it. Yep. Any other questions? All right. Epoxides. So in epoxides, you're giving us a good nucleophile. So is that going to attack the most substituted or least substituted? Right, so it should attack the least substituted. So if that's the case, we're going to end up attaching this group over here. And then since, yeah. Oh, on the WordPress? So the one on the WordPress is not modified or anything. So there's some questions that I did add later on, like before last Thursday, I think, that are not going to be on that file. Okay, so if you're looking at it, it might not be there. I added like a lot of more questions. Good point, thank you. Okay, so going back to this, we have the epoxide. We're going to attach this least substituted side. And then since it's an SN2 reaction, there's going to be inversion happening. So just going to draw it over here. Then they're giving us ethanol, which is going to go ahead and hydrate this. All right, so what would the answer be? I believe so. Any questions? Right, so it's starting on a dash. And so since there's inversion, that's why we're going to end up having the group we're adding on a wedge. Yeah. Mm-hmm. So that's why we're going from a dash to a wedge. So that's pretty much what's happening. So if this was on a wedge instead, then whatever you're attaching should end up on a dash. Yep. Any other questions? All right. Okay, so what is a major product of the following reaction? We have this going on, so Br is a good leaving group, that's going to end up leaving, and then this is going to be negatively charged, so it's going to get rid of a hydrogen, right? So we're going to take away that hydrogen, it's going to form a double bond in the structure. So what we're going to look at is seeing if it's going to make it fully conjugated, if it's going to take away the hydrogen that's right next to where the bromine is, and how substituted it's going to be, because we want the major product, all right? So can this happen? No, right? So we can automatically take out that. Can this happen? Right. So it's going to be between B and D. And then if we look at both of them, which one is more substituted? So they're both equally substituted, but then which one's going to give us a conjugated system? B. Right. It could, but then since they're giving us the answer trays as elimination, then we just worry about that. But it could do substitution as well, because we don't have like a bulky base or anything, so it could undergo that. It could be like a major minor product kind of deal. Yes? Right, that too. That's a good point. So if it was primary, then it would go ahead and do substitution instead of elimination. Thank you. Although substitution does happen, I know like in class they said it doesn't, but it should at least as a minor product. I'm sorry? I would say so because it's tertiary. Any other questions? Yeah. Why not C? Because if we compare C and B, this one doesn't give us like a fully conjugated system, but this one does. So this one would be better because you have the double bonds right next to each other. Like one carbon away. Yeah. Yep. Any other questions? All right. So what would be the major product of the dehydrohalogenation of 2-chloropentane by KOH? So 2-chloropentane. Chlorine is going to leave. And then that should be the answer, so then we just have to compare it to these guys. So which one satisfies that? Yep. That should be the answer. Right. So I usually base it off of the answer choices, to be honest, because I don't want to memorize every single reagent or anything, or at least that's how I approach it in the ACS. And then as far as you know how like mechanisms go, and knowing that halogens are usually good leaving groups, that a negatively charged OH can go ahead and take away hydrogen from a structure, then you should be fine. Knowing where the arrows go and stuff is really useful. Any other questions? Yeah. That's a good question. So why not this one? Right. So they're asking us for the major product. So it could do that, but then since we want the major product, we want the one that's more stable and more substituted. So that's why it's the one in the middle. Yep. Yep. Any other questions? Yeah. It's a good leaving group. So as a halogen, if it leaves with that extra pair of electrons, it's fine by itself having a negative charge. Yep. Any other questions? All right. So, okay. What reagent could accomplish this reaction? Let's see. So we're changing this iodine for N3. And then iodine is part of the halogen, so that's going to be able to leave on its own. If that's the case, all we need is something that's going to replace the positive charge that iodine is going to leave behind. So if we look at our answer choices, this is a spectator ion, this will make a negative, and therefore this is going to be able to go ahead and attack there and replace the iodine. So that's why it's D. Yep. So, if we were to do a methyl shift, it's still going to give us a secondary carbocation. I know what you're saying. Like a 1,2 hydride shift to leave it over here. That's a good point. I would assume it wouldn't form the carbocation intermediate then, and it would just like have it on the same step, just to avoid that. So since we have this as a negative charge already, then it could go ahead and do it on the same step. But then iodine is going to leave and then leave like a partial positive there for you to attack. Yeah. Right, so you avoid like the formation of a carbocation and the shift therefore. Yep. Any other questions? Yeah. Should be SN2. If it was SN1, then it would, as we were saying, it would form a carbocation. And then she pointed out that it could form, you could have a 1,2 hydride shift, for example, and then we wouldn't be adding that N3 where we want it. So if it was on the same step, it was unimolecular, then it would do that. Yep. Any other questions, guys? All right. right, so which carbocation would not be likely to undergo rearrangement? Just by looking at it, I would go with C, just because it's already tertiary. Does that make sense? Any questions? Yeah, so we already have a carbocation and a tertiary carbon, so there's no really no need for us to do rearrangement. On A, for example, though, it's on a secondary, and we have this methyl right here, so we could do a 1,2 hydride shift, and we can put it over here instead. But then this one you really don't need it because it's already tertiary. Any other questions? All right. Which is a proper representation of the flow of electrons in this E2 illumination? So if we look at A, OTS is a good leaving group because initially it was an OH, then you toss it that you form OTS. So that leaves. This base takes a hydrogen, forms a double bond. That looks right to me. So far I'll go with A. This is never going to happen because your OTS should be leaving, so that arrow is incorrect. This is also incorrect. You're never going to see hydrogen attacking something else, so that doesn't make sense. On this one, this is not showing us taking away the hydrogen, so that's wrong. And then for this one, it should all be on the same step because it's E2, so that's why it's wrong. So the correct answer is A. Any questions? It's incorrect because it's an E2 elimination. So when it's E2, it should only be on one step. Kind of like SN2, how it's only on one step. And then here they're showing it on two steps, so that's incorrect. Any other questions? All right. All right, so this reagent is for what reaction? Yep. So we know we're going to do hydroboration oxidation. Then as I was saying earlier, if it's hydroboration oxidation, it should only be syn addition. So we're going to add both the OH and the hydrogen on the same side. So if it's hydroboration oxidation, it's syn. And so we're going to add, in this case, D and OH, because they're giving us B2D6 instead of B2H6 on the same side. So if that's the case, A is adding OH and D on the same side. B is also doing the same, but it's also anti-Markovnikov, right? So it's syn and anti-Markovnikov. These are adding on opposite sides, so it's not C or D. So between A and B, which one is anti-Markovnikov? A? I heard A and B. So we want our OH to be on the less substituted side, therefore it's A. If we were to add it here where the CH3 is, then it would be more substituted. Because hydroboration oxidation is anti-Markovnikov, always. I think it's probably the only reaction that I know so far that's anti-Markovnikov. It's always the OH. Mm-hmm. Any other questions, guys? Okay. Okay, so this reagent is to do what? Hydration. So in hydration, we're pretty much adding the same thing that we would add in hydroboration oxidation. So we're going to add an H and an OH. But then in this case, we're not worrying about anti-Markovnikov. It's going to be Markovnikov. So our OH is going to go on the more substituted side. And then I'm just going to rewrite it here. All right, so I'm going to draw the full mechanism just so we can show how we're going to do the tautomerization at the end. All right, so we have the acid first. Yeah. Okay, that was a lot. So can you guys see everything there? Yes? Okay. So on the first step, we're going to use the acid to go ahead and protonate that alkyne. Once we do that, we're going to add hydrogen to the less substituted side because we want the OH to be on the most substituted. So that's why it ends up over here. And then we use water to attack right there, giving us that OH group that we want once we depronate it with the acid to restore it. So we'll restore the acid. Once we get the acid restored, that double bond can go ahead and take a hydrogen again from the acid, giving us this structure over here, and it gives us a positive charge down here. So in order for us to neutralize that positive charge, we use a lone pair from the OH, resonates down, and then we get this compound over here. But then since this oxygen has a positive charge still, then we can use the acid again to restore it, and then we get this ketone. Yes? Sorry. So, I don't know if it's just in the presence of, kind of like as a solvent, because it wouldn't, I don't think it plays an important role in the reaction itself. So it could just be there as a solvent. That's what I would assume. Any other questions? This step over here? Because we have a positive charge right there. So in order for us to make that neutral again, then you form the carbonyl carbon, and then with more acid you can go ahead and deprotonate it. The base form of the acid. Yeah. I'm going to move this really, really quick. Hydration. Yep. Okay. Does that make sense? And then from there we got the product, so all we have to do is compare our answer choices. So these have OH, so that's out. This one's an aldehyde, that one's a ketone, we got the ketone. Yeah. For that one? same thing. Yep. But then in this case, since they're giving us B2D6, then you would add a deuter, I don't know how to say it, but that isotype of hydrogen instead of hydrogen. Yep. Any other questions? All right. This should look a little familiar because it was from Orgo 2. So for the mechanism, this is our what? Is it the diene or dienophile? Diene. That's our diene. This over here is our dienophile. Whoa. All right. And then for the arrows, just get that. We're going to form a 6-membered ring. In this case, let's show it on like the chair conformation kind of. So this automatically goes out. We're in between these 3 choices. So this carbon over here is going to go up and form that bridge. So these all have that right. But then what we're looking for is a major product. So what would make it more stable? Having both of the substituents endo. So it's a little different. So endo. So we want both of them to go down. So it should be B. Yeah. Yeah. So we want the major product, so that's why when we form the chair, we want our substituents to be looking down, which is the endo product.
So the major product always have both.
Mm-hmm. Yep, because it makes it more stable. If it goes down in any other way, it's endo? What do you mean?
You said endo is like they point down.
Yeah.
What's the
Exo. So if it's exo, it would be pointing up, closer to the bridge that we form. Good question. Any other questions? All right. Yeah. All right, so this is another hydroboration oxidation. So as we said before, our OH is going to add to the most substituted side. Just kidding. Least substituted because it's hydroboration oxidation. So we're going to have OH adding over here. And then when we do the reaction in the mechanism, we're going to end up tautomerizing it because we don't want the enol form. We want keto because it's more stable. So if that's the case, we're going to end up with an aldehyde. So if we look at the options, the only one that's an aldehyde is C. Does that make sense? Yes, so since this is only an H over here and we don't have any more carbon groups, we're going to add the OH to the less substituted side. So we're going to add it on this carbon, right? And then we want to tautomerize it to the keto form because it's more stable than enol. And then when we do that, we get the aldehyde. So that's why it's C. Can I move on to the other question? Yeah. Yes. So this is hydroboration oxidation. OH is going to go to the left substituted side. When we add that OH, we're going to resonate it to form the keto form, which is more stable than enol. So when we do that, we get the aldehyde. Yep. These should look familiar as well. It's kind of recent. So what is the principal product of acid catalyzed reaction of cyclopentanone with ethylene glycol? So cyclopentanone looks like that, and then we're going to react it with ethylene glycol. The reaction is actually pretty long, like the mechanism, so I don't know if you guys want me to go over that because we don't really have that much time, but as long as you know that when you're reacting a ketone, you get this. When reacting with ethylene glycol, you should be solid. They're not going to ask you for the mechanism at all. If you guys want me to go over, I can go over it, but I don't know. What's up? Yeah. I think you had a question? Right. They also use it as a protecting group. So if you see it as in a synthesis, then you can protect something using that, and then deprotecting it by making it go back via hydrolysis. It's a good point. Any other questions? Actually, I think I have the mechanism like written if you guys want to see it, but it's kind of long and annoying. Let me see. All right. I'm just gonna show you. It's I don't know if you guys can see that, but it's that. If anything, just if you want to like refresh your mind a little bit with that. Does it look familiar? Okay. I'm gonna move on. Yeah. The only thing they might ask you is like saying which arrow is incorrect or something like that, but you don't actually have to like write anything down. So knowing like the flow of electrons and what attacks what and stuff like that, then you kind of need to know, and knowing if it's correct or incorrect. Yeah. Spectroscopy, I remember there being a good amount, to be honest. I asked Fraser, he said there's usually like 2 or 3. Sounds reasonable. When I had it, had like maybe 4 or 5, so a little more. So as long as you guys know like the basic readings, like knowing what a carbonyl looks like in IR, amino groups are pretty important as well. Maybe carboxylic acid and OH, like the basic ones, you should be fine. Nothing too crazy. Also, HNMR, knowing splitting patterns is also important. CNMR, knowing like how many readings you would have in CNMR based on a certain structure. That's important. I'm sorry? I don't think you need to know that. Yeah. There is polymers as well. So I know Fraser didn't go over it. Dowdy did, if anyone hears from Dowdy. But I saw polymers, like 2 questions.
What about nucleophilic, substitution, and electrophilic?
Nucleophilic and electrophilic?
Substitutions, yeah.
You'll see that, for sure. That's Orgo 2. All right, I'm going to move this out. All right, so for this question, the answer should be A. Next question. It's pretty much the same exact question, but the reverse of it. So whenever you want to get rid of this, as we were saying before, as a protecting group, then you would just hydrolyze it and you go back to the ketone. So you should get that answer. Because we get ethylene glycol again, and then the ketone. So it's pretty much the reverse of the reaction I just showed you guys. Any questions? All right. All right, so which would be the best reagent for this conversion? So if we were to use A, OH is just going to go ahead and attack the carbonyl carbon. It's not really going to do much because you can't replace that OH or make it leave. Okay, so it's not A. This is just a reagent to dry stuff in lab. So I don't think we've seen it doing any reactions in class. In lab settings, and it's just to dry any aqueous stuff on your beaker or whatever. So this is not the answer. And then for this one, same thing. This is a weaker base than this is, so this is not going to be able to leave by itself. So the only thing you could possibly do is replacing this OH for a Cl using this reagent. And then once you do that, you can use another equivalent of this to attach it to your leaving Cl group. Does that make sense? It's kind of newer material. Yep.
Why is it for 1.5? Like, shouldn't it just be 2 equivalents of that then? If you're just doing it for
I know what you mean, like half a molar equivalent. To be honest with you, I don't really know why they say that, but it is like another equivalent of this for you to be able to attack it again. Yes. Who wants to go first? All right. Yeah, so you would make it a Cl and then you just use like another equivalent of this to attack it. Yep. Yeah.
So for the structure of the ACS, is it
It should be all over the place. I don't remember there being like Orgo 1 and then up to Orgo 2. It's a little annoying. Yeah. Okay. All right. Any questions about this particular question? C and D. Okay, so for D, my bad, you would be using where you're going to use eventually on this one to attack, but then for this one, if you don't make it a CL first, OH is not going to be able to leave by itself. So that's why you have to convert that carboxylic acid into a acid chloride for you to go ahead and make that chloride leave and then attach. So pretty much the main difference between these two is that this one will give you a good leaving group, this one doesn't. Good? All right. Okay, so what is the best way to perform this transformation? We're basically adding this group right here. So if we look at A, this is going to be negatively charged. This can go ahead and attack the carbonyl carbon. When it resonates back down, this group can leave, replacing this for that. So it's A. Let me just check how many questions we have left. Okay, so we have a good amount. Is that good? Can I like move on so we can cover more? Okay. Next question. Identify the reagent that is best suited for the conversion. So as we learned this semester, if we use either this one or this one, it's going to be very strong, so it's going to make this go all the way to an OH. That's not what we want. So these options don't work. Okay? And then this one, it's going to attach an oxygen to it, and that's not what we want. So automatically it's out. This, however, is weak enough for it to stay as a ketone instead of as an OH. So that should be the right answer. Does that make sense? I'm sorry? Because it's Gilman, so it's weak enough for it to go back to the ketone and just stay as a ketone. If it was a Grignard reagent, it would just continue to attack until it forms the OH. Good? Cool. For 15, we're keeping this side the same. We're just going to change this group over here. So instead of the carboxylic acid, we're going to have this amide forming right here. So if we look at the first one, SOCO2 is going to make OH a Cl. And then if we use this amine to attack with its lone pairs, then it should give you the product that you want. Pretty straightforward. As long as you guys know what each reagent does, you should be fine. These are pretty recent from this semester. And that's pretty much what you're going to see in the ACS. They're probably going to use more reagents from Orgo 2 than Orgo 1, which is good, because you should be fresh on that. Yeah. Yeah, so SOCO2 is just going to replace this OH into a Cl. And then once you do that, you can use this amino group to attack the carbonyl carbon and attach this group. Oh, so in the ACS, you're probably going to see more reagents from Orgo 2 than 1, from what I remember. It could be different. At least last semester, that's how it was. I saw way more things from Orgo 2 than 1. Although it's kind of like evenly distributed, there was a little more Orgo 2. Yep. Cool. All right. What is a product of this reaction? This is kind of like a synthesis problem. They're just giving you the reagents, so as long as you know what each reagent does, you should be okay. So for the first one, we have Cl leaving. Nitrile is negatively charged, so we can replace that. So we're going to end up with, at least for the first step, that's what we're going to have. And then after that, we're going to do hydrolysis. If we hydrolyze that, what do you guys remember? What do we get? Yes, so every time you hydrolyze a nitrile group, you're going to get carboxylic acid, no matter what. So therefore, the answer is A. This makes no sense. This one doesn't make sense. This one is missing a carbon. Say that again? Yeah, so when you do hydrolysis on a nitrile group, you always get carboxylic acid. There's a full mechanism for it. If you guys want to see it, you can take a picture. I have it written. It's just long. I don't think we have time. But I don't know if you guys can see that. But it's this part right here. The important part about this whole thing is just doing the last part of hydrolysis, which is kind of not that intuitive. You guys all got that? All right. This should be pretty familiar as well. So we're going to use this to form the enolate. So if we look at the left of this structure, we have a benzene ring, so there's no really like any hydrogens that we can take. So it's going to take the hydrogen from this side. So I'm just going to draw it. We have the enolate right there. And then if we use, just kidding. If we use this, which kind of looks like water, that enolate can take that, and we end up forming this compound right here. So if we look at our options, the only one that looks like that is B. Does that make sense? Any questions? All right. Whoa. Okay. The answer for the previous one was B. All right, for this question, we have two equivalents of that. OH is going to form the enolate again, so we have just going to flip it. And then we have another equivalent of the same structure, so that should be it. For Dr. Dowdy, I know he always went all the way to the unsaturated compound. Actually, no, for Fraser, he went all the way to the unsaturated. For Dowdy, he didn't. So for Dowdy, he specified that if you were in room temperature or in high temperatures, then it would go all the way to unsaturated. For Fraser, he always made it go all the way. So just keep in mind, in this case, they don't really give you any temperature conditions, so that's why it stays like that rather than the unsaturated compound. Okay? But I'm doing enolate. They're giving us a pretty strong base, and then we have alpha hydrogens going on. So that should give you a hint enough for you to know that you can deprotonate it. Also looking at the answer choices. So if that helps, if you need to like draw every single answer choice, just kind of like visualize it, then I would do that. That's what I did. Yeah. So if they give you if they don't say anything, for Dowdy's class at least, if he didn't say that there was any specific temperature, then you would just assume room temperature, and he would make you go all the way to unsaturated, In this case, it didn't really say anything, so it could be either one, but they don't really give you anything with unsaturated compound as an answer choice. So that's why leaving it in OH is fine. If they say it's cold and then you have like the one with the OH and then the unsaturated, then you would keep OH. If it's room temperature higher, then you go all the way unsaturated. Just something to keep in mind. Shouldn't do that to you guys, I don't think so. It's kind of mean. Good? The answer should be should be that. All right, so here's an IR question. I'm gonna let you guys look at it really quick. I'm gonna like distribute these surveys for you guys to fill out. So kind of like work on it, and then when I come back, we can just go over the answer. Give it to you, pass it down. Hey, what's up? Yep. What's up? Yeah. If you want to stay longer, I can like help you out with any specific questions. Yep. Oh my God. Thanks. That should be 3. Yep. Did you just walk in? Oh, okay, okay. I'm just gonna keep you guys a pile. All right, so just make sure that before you leave, you just give me back the survey, and then you can leave. So for this question, which compound is consistent with this IR spectrum? So we just kind of have to look at the peaks. We have one at around 1600. So what should that be? Carbonyl. Everything before 1500, do we look at? No, right, because it's a fingerprint area, so it doesn't really matter. Unless on the structure that they're giving to you, you have an ether, then that could be in fingerprint, so just keep that in mind, okay? What else are they giving us? We have carbonyl. We don't have anything for nitrogen over here, so this can go out. This one doesn't have carbonyl, so this one's out. Between these two, this one's a carboxylic acid, but we don't have any readings for carboxylic acid right now. That goes out, the answer should be B. Does that make sense? So pretty much know those basic readings, no carbonyls, carboxylic acids, OH, aminos especially. They can trick you with that. Benzene rings. That should be pretty much it. Yes? 3000 peak. That should be your CSP2 hybridized carbons. CSP3, yep. Any other questions? You got a question? Yeah. How did I figure out what? Sorry? The answer? Okay, so for A, we know that 1600 is a carbonyl, so we want a double bond carbon with an oxygen, okay? A doesn't have one, so we can automatically take it out. And it has an OH instead, but then OH would have a really broad peak over here and we don't have that. So that's why I know it's not A. For C, you have carbonyl, which is what we need, but then you also have nitrogen. And then nitrogen, when you have nitrogen, you would see a reading over here as well, but we don't have that. So A and C can't be it. For D, you have a carboxylic acid, and then that should usually give you a peak like that's really broad and strong, but we don't have that either.
Can you write out the spectrosities for like if you saw alcohol or a ion?
Can I draw it?
Like just the numbers, like we know if 1600 is carbonyl and carboxylic acid would be what number alcohol?
I don't know the exact numbers, to be honest with you, but I know alcohol should be like 3200 to maybe 36, and it should be strong. So it should be white and strong. Carboxylic acid looks the same, but it's a little more exaggerated than OH. So it should be around the same range, but it should be kind of like that for carboxylic acids. And then for this amide, we're going to see one later on that kind of looks like that. Any other questions? All right. Next question. So, which structure is consistent with HNMR spectrum? So, all of our readings are singlets. How do we know they're singlets? Exactly. So, we only have one peak. If it was split, then it would have many peaks. So, if we look at all of the structures that we have here, we could eliminate something if it doesn't give us all singlets. So, in this case, these carbons are going to split each other, and they're not going to give us a singlet reading. So automatically B and C can go out. Does that make sense? So if I were to draw this, and then this one, these right here are going to split each other, so this is going to form, this is going to be a triplet, that's going to be a quartet. And same thing here. But then when we look at HNMR, we don't have that. All right, so that's why I can immediately eliminate B and C. Between A and D, then we have, let me see. I'm going to draw them. All right, so they should all give us singlets. This is not going to be split into anything because if we look at the adjacent carbons, none of them have hydrogens. This one, same thing. And then the ones on the ring are going to give us the same reading because it's symmetric. Same thing for this one. It's symmetric. This one's going to be a singlet. This should be a singlet as well. All right, so the HNMR for the whole ring should be the same reading. These hydrogens over here are going to be the same reading. These hydrogens over here are going to be the same reading. So now what we have to look at is shielded and de-shielded. Okay, so if we look at the hydrogens on these guys, this one's further away from the ring. Therefore, let me think. For this one? Why does it have 3 peaks? So for A, you have the hydrogens here. You have 2 here. And then you have the ones on the ring. But then since it's symmetrical, that's why the ones on the ring are going to be 1 reading. And then same thing for this one. So you have the hydrogens from here, the ones on the ring, and then the ones from here. So they both give you all singlets, but then you have to look at shielded and de-shielded. So shielded is when what happens? Say that again. Shielded. Shielded you should be donating, right? So you should be giving it Electrons de-shielded, you're taking away. So on these hydrogens over here, for both of these cases, are they being shielded or de-shielded? De-shielded, okay, right, because there's nothing really donating electrons to that, so these guys should be de-shielded. If that's the case, then it's going to be more to the left of our HNMR, all right? If we look at these guys, they are next to this oxygen, which should make it kind of shielded because the electrons are could donate electron density to the hydrogens, meaning that it would be more shielded, right? And then for the benzene ring reading, it is typical to see it over here on like the 7.5 area. So they both have that reading, but then these are more shielded than these over here. Okay, therefore the answer should be, let me just make sure, I don't want to say the wrong thing. Yeah, so it's A, because we have shielding over here for these hydrogens, yeah. These over here. So I'm just going to erase it because it looks messy. All right, so when you're looking at splitting patterns, you're going to look at the carbon that's right adjacent to the one that you're analyzing. So if we look at this one, the carbon adjacent to it has 2 hydrogens. So therefore, these hydrogens are going to split this into a triplet, which I think I had to mix it up. But since you have 2 hydrogens here, you use the n+1 rule, n being the number of hydrogens that you have. So in this case, you have 2, so 2 plus 1, 3. So these hydrogens are going to split this over here into a triplet. Okay? And then for these, you look at the carbons adjacent. This one has an oxygen, so you don't have anything to split it with. But then if you look at this carbon over here, it has 3. So n+1 again should be 3 plus 1 equals 4, making this a quartet. I think I had a flip-flop before. Yep. These are more shielded because you have this oxygen donating electrons to it. So that should be this reading actually, because it's more to the right. But then on this one, you don't really have that going on. You only have the ones on the benzene ring, this methyl, and then this over here. Any other questions? All right. Okay, so this is the one that I was talking about, the nitrogen reading. So we have, can barely see it, but this is 1600. Yeah. Everything before that we don't take into account. We have this sp3 reading over here, and then the only compound that's giving us an sp3 reading is this guy. Okay, and then they're also giving us these 2 peaks for the amino group. And then usually if it has 2 peaks, then we know it's a primary amino. If it only had 1, then it would be a secondary amino group. Does that make sense? So 2 peaks. There's like an 80% chance that that's going to be on the ACS. It's pretty typical. So if you have 2 peaks over here, then it's going to be a primary amino. If it was only like 1 peak, then it should be a nitrogen with some methyl or something attached to it. It should be secondary. Does that make sense? It says 2 peaks for amino region means that you have a primary amino. Any other questions? Yeah. Yeah, the 3000 peak, that's like the only importance about it. Because like everything else is just going to give you an sp2. Any other questions? All right. All right, so the next one actually shows the carboxylic acid reading. So it's usually like super big and bulky. So if you see that big, massive mountain-looking thing, carboxylic acid automatically. So if we look at our options, there's only one that gives us a carboxylic acid, so that's automatically it. Does that make sense? All right. Any questions about the previous two questions? Cool. Yeah. If it's one peak, then it means that you wouldn't have those two hydrogens attached to it. So if we look at the actual answer, you have two hydrogens. But then if it had one peak instead, then it would be maybe something like that. Instead of a hydrogen, you have a methyl group or something. Yep. Any other questions? Yeah. For that one, because the only one that gives us the CSP3 region, which is over here, is D. So that's why I can like automatically eliminate everything else. Because we have CSP3 and CSP2 readings in this region over here. CSP3. Okay, so I wrote down that it's from 2,850 to 3,000, and it's usually very strong and narrow. So that's why we know it should be D. Yep. Any other questions? All right. Okay, so which structure is consistent with this H&MR spectrum? So on this one, we actually have splitting going on. So if we were to draw everything, so for okay. So we don't have to do all the splitting patterns. I'm just going to tell you guys straight up that the answer is B. So if we look at B, we have, this should be a singlet because there's nothing that can split it. So that should be equivalent to this reading over here. So that's going to be our singlet. These guys are in the same, they don't have two readings for it because it's symmetrical. So only one splitting pattern should be enough. All right, so for this over here, that should be a quartet. So a 2H quartet. This one should be a 3H triplet, which is what we see over here. So this is our triplet. That's the quartet. And then every other option also has triplets and quartets going on, so it goes back to kind of like to the previous question where you have to see whether it's shielded or de-shielded. Okay, so the one with the singlet, resonance structures can actually donate some electron density to the hydrogen, so that's why it's not as de-shielded as any of the other options. Okay, so that's why it's more towards the shielded side of it for our singlet region. For our quartet, which is right next to oxygen, oxygen is very electronegative, so it can take away electron density from it, so that's why it's de-shielded. And then for the triplet, which is over here, it's further away from that oxygen, so that's why it's more shielded. So when it comes to location, you just have to see how close it's to like an electronegative atom or how far away it is from where you're looking at. Yeah. Deshielded is left of the graph. So yeah. Nope. Can't remember what it means, to be honest, but it doesn't mean anything. You don't have to worry about it. Yeah, which is, I don't know, I don't remember. Say that again? Is it? Oh, I don't know. I really don't know. All right, cool. So we're kind of running out of time, but next question. Which reagents are best suited for this transformation? So we are reducing this bond over here. So that goes back to reducing agents, knowing what they're selective for. LiLH4 usually reduces everything, so we're probably mess this up, which we don't want. So no. I haven't seen this being used as a reducing agent, so no. H2PDC is usually selective for alkenes, so that should be the answer. NaNH3, as far as I know, is actually selective for ketones, as that's not what we want to reduce, so that's why it's wrong. Any questions? All right. We're almost done. So which sequence of reaction is expected to give the best yield of 3-nitrobenzoic acid? So these guys are gonna ortho-para-direct because they're electron donating. But then if we start with a withdrawing group, it's not gonna really undergo anything. So that's why we don't want A. Although it's a meta-director, which is what we want, it's gonna deactivate that ring, so we're not gonna be able to add stuff to the ring. So if we look at everything else, we needed to meta-direct our nitro group. So if we were to do oxidation on this, we would form a carboxylic acid, which is not as deactivating as nitro. And then once we form the carboxylic acid, we can add that nitro group using this reagent. So that should be the answer. Does that make sense?
So NO2 is so deactivated that you wouldn't be able to?
Right, usually, from what I've seen. Any other questions? Cool. And then I think that's the last one. So okay. So the first reagents came in a 4-NaOH in heat. So if we use that with a methyl group attached to a benzene ring, every single time we're going to make carboxylic acid. So for that first step, carboxylic acid. Second step should be bromination. So if we form a carboxylic acid, it's going to meta-direct that bromo. So the only one that's doing that is A. And then meta-direct bromo. For the third step, it's going to make that OH in our carboxylic acid a Cl instead. Once we do that, they're giving us a secondary amino group. So Cl is going to leave. This can replace the Cl. Therefore, the answer should be A. Does that make sense? Okay, there should be a couple problems on synthesis like that. They will give you all the reagents, and then all you have to do is follow each step and get to the product. There should be around 10 questions on the ACS. That's pretty much all I got. There's only 5 minutes left. I had extra questions, but I don't think we have time. Yes? So on step 4, the lone pairs on the nitrogen are going to attack the carbonyl carbon, and then Cl is going to leave. So you're pretty much going to replace Cl for that group. Yep. Just make sure you guys give me back the survey, please. And then if you're like having snacks or anything, just make sure you take them out with you. Good luck on the exam.
Here you go.
Thank you.
So, oh, go ahead.
Do you need to put anything on top of here? You got that.
Wait, say that again?
Do you need to put anything up here?
I
Or
don't
just
think
leave
so.
that
I think you're good.
Okay.
Yep.
Hey,
Yes.
so that PDF that you sent me, is that like the same thing as I would get if I bought the official ACS? Okay.
That's what I studied from.
Okay.
And like a lot of the questions come from here. For like all the people that did tutoring for the ACS, we all got questions from that thing
Okay.
that I sent you. Yep.
Okay, cool.
Yep. Thank you guys.
Thank you. Question.
Yeah.
The final is Thursday. I'm with Frazier on Tuesday and Thursday. Do you know anything about it? 'Cause I'm like confused because
I'm actually
And the
confused too because I
AC
have to proctor for him, but I don't even know when the day is.
yeah, because the ACS
Thank you.
is like the same day too. I don't know. I'm gonna.
Thank you. Thanks.
Oh, thank you though.
Yeah.
Is there
Thank you guys.
are the questions online somewhere, or did you just?
So part of it is online on the UCF